I want to do a little introduction with you to kind of show you what we're doing and what it means. So, we're going to talk about Jack and Diane. They're going to help us. Last year, Diane and Jack were the same height. So, let's talk about some possible heights they could have been. Uh, we can plot any points that we think make sense in this situation. Um, it doesn't tell us if they're talking about centimeters, inches, feet. So let's just pretend we're dealing with giants here. All right. Jack and Diane could both be 2 feet tall, do you think? So, like, Diane would be 2, Jack would be 2. What if they were both 5 feet tall? Here's Diane 5, there's Jack 5, there would be the point. What if they were both 9 feet tall? Go to 9 on Diane and 9 on Jack. So, do you see that this is the line it would graph? And every point on this line is a possible height for Jack and Diane. Now, they could be half, they could be 2.5 feet and 2.5 feet. The reason I connected it, that it's continuous, is because they can be any part of a foot in between, a centimeter, an inch, a part of an inch, anything in between. So write an equation. If x is Diane and y is Jack, well, their heights are equal, right? So the equation is y equals x. Their heights are equal. This actually is what we call our parent function. We're going to talk about that more later this week. But our parent function, linear parent function, that's the basic one where what's the y-intercept? And it's 0, 0. And then the slope there's an imaginary 1. So up 1 over 1. Let's look at case 2. So there's our line that represents y equals x, that their heights are equal. Let's look at case 2. Case 2, this year Diane's taller than Jack. Let's give some possible heights. So what if Diane was 2? She's taller than that Jack, so maybe he's 1. Maybe he's 1.5. What if she were 4 and he were a half, or he were 2? What if she's 5.5 and he's just 5? What if she's 7 and he's a half? She's 7 and he's 2.5. 7 and he's 6. Are you getting the point that I have all of these possibilities? Diane could be 5.5 and he could be 1.5. Diane could be 6. He could be 3. All of these show that Diane is taller than Jack, right? So Jack's height, Jack's y, is less than Diane's, right? Jack is shorter than Diane. His height is less than Diane. Can it be equal to Diane? No, it cannot be that line that we just did up there. So what's the line we just did? We did y equals x. Diane equals Jack. And it was started at 0, 0, and it was up 1 over 1. I'm going to dash that line because they can't be equal. She's taller, so they can't be equal heights. So I'm going to dash that. But look at all the possibilities down here. Their heights can be anywhere down in here. We just proved that by showing all the points down here in all this area, all these points. Jack is shorter than Diane. So, couldn't we shade this to show that every point down here in this shaded area is a possibility and makes this true? I just wanted to introduce this to show you why we shade, what the shaded area of an inequality means, what it represents. And the reason this line is dashed and not solid is that the points on this line cannot be a solution. This shaded area is called the solution set. There's no solution on the dashed line because they can't be equal. Their heights are not equal. Jack is shorter. So on the line, the y equals line, it can't include it, so y is less than x. So here's the graph of an equation, y equals x. Here's the graph of an inequality, y is less than x.